Welcome to this video exploring how graphics cards work by delving into the world of GPU architecture. So what exactly is a GPU? Let's explore how graphics cards work and the technology that drives them. A graphics card, or graphics processing unit, is a specialized processor for parallel computation. It is a parallel processor found in PCs, laptops, and servers, primarily used for graphics, AI, and computing, and is made by companies like NVIDIA, AMD, and Intel. The core difference between a CPU and a GPU lies in their design. A CPU uses a few powerful cores, whereas a GPU utilizes thousands of smaller cores, showcasing two very different design philosophies. CPUs have few large cores, like 8 cores running at about 5 GHz each, specialized for serial task execution. GPUs, conversely, utilize thousands of smaller cores, designed for massive parallel execution of simultaneous tasks. Modern displays demand massive computation. A 4K frame needs 8.3 million pixels, rendering at 60 or more frames per second, results in a raw workload exceeding 500 million operations per second. A CPU with only 8 cores simply cannot handle this in real time. Parallelism solves this by treating a single frame as a massive job to be solved by many tiny workers. Each GPU core processes its own slice of the frame simultaneously. SIMD stands for Single Instruction, Multiple Data. This means one instruction is executed across many different data points simultaneously, producing multiple results all at once, which is essential for rendering efficiency. The GPU architecture is built around streaming multiprocessors, or SMS, arranged in a grid. A single GPU chip can have 24 to 150 SMS, each containing 64 to 128 cores, totaling around 10,000 cores on the whole chip. The streaming multiprocessor is the basic building block of a modern GPU. It contains CUDA cores, which are tiny arithmetic logic units for floating-point math, and a warp scheduler that dispatches 32 threads, known as a warp. Threads, warps, and blocks organize the thousands of cores. A thread is one unit of work, like computing one pixel's color. A warp bundles 32 threads running the same instruction. A block is a group of warps sharing fast L1 or shared memory. The GPU memory hierarchy moves from faster and smaller to slower and larger as you move away from the core. Registers are the fastest but smallest, followed by L1/shared memory, L2 cache, and finally the largest but slowest VRAM. The graphics pipeline transforms a 3D scene into a 2D image through 6 main stages: vertex, transform, rasterize, fragment, test, and output. The critical feature is that each of these stages runs on thousands of cores in parallel. Stage 1, the vertex shader, involves positioning the corners of every triangle. It takes the 3D coordinates per vertex, performs matrix multiplication, and outputs screen coordinates. This is performed for the millions of vertices in modern games. Stage 2 is rasterization, which is the process of filling triangles with pixels. The GPU determines which pixels are inside each triangle in parallel, a necessity given the millions of triangles processed per frame. Stage 3 is the fragment shader, where the color of each pixel is computed. It takes inputs like texture, light, and position to output red, green, blue, and alpha color values for every single pixel in parallel. Stage 4, the frame buffer output, is the final stage. The finished image, called the final frame, lands in VRAM and is then sent to the display 60 to 240 times per second, depending on the monitor's refresh rate. Data transfers from the CPU to the GPU primarily over the PCIe bus, a high-speed interface, typically PCIe X16. Vertex data, textures, and shader programs all flow across this interface to the graphics card. Beyond gaming, GPUs are the engines behind modern AI, science, and high-performance computing. Their parallel architecture makes them ideal for tasks like deep learning, fluid dynamics, and cryptographic hashing. Key GPU specifications include VRAM size, boost clock speed, FP32 compute, TFLOPS, power draw in watts, the number of cores, memory bus width, PCIe interface version, and memory bandwidth in terabyte per second. The GPU delivers high frame rates for smooth 4K gaming and is AI-ready, powering models like Stable Diffusion. Its scalable parallel architecture ranges from integrated laptop GPUs to powerful data center accelerators. A good analogy is building a house. The CPU is one master builder, smart and versatile, but only working on one job at a time. The GPU is an army of bricklayers, specialized for laying bricks but completing the wall instantly. To recap, GPUs use thousands of small cores, leverage parallelism, employ the SIMD concept, are structured around SMS, follow a graphics pipeline, and rely on fast VRAM and PCIe for data movement. Thank you for watching this deep dive into GPU architecture. If you enjoyed this video, please consider subscribing for more content like it. See you in the next one.